right? Now, so the first quantity I asked you what is VM, right? We don't know. We need to find out. So here I'm going to do some tedious math, and so you know how to find the VM of a transistor. But why we want to do this? This is because then you know the equation. You have some insight how to change the VM, right? So at VM, whether it's at VM or not, but we know that it's always true INP equal to negative, sorry, IDP equal to negative IDN, right? I will say that already. And also, we know V in equal to V out equal to VM by definition. So all I need to do is just write down the equation I already show you here. And because VM, we just study, they must in saturation. So I'm going to use saturation equation. Okay. So I just want to conform to my notes. So I will say this instead, right? IDN equal to negative IDP. So on the left, I'm going to write IDN K dash W on L VGT V mean. What V mean should I use now when it is in saturation? Don't know, right? Because I did not tell you whether it's pinch off or velocity, but let's assume velocity saturation for our technology. So because of that, that will be VD set minus VD set squared divided by 2. That is the IDN, right? And here I'm going to ignore the channel length modulation. Also for the PMOS, right? As I told you, I like to use absolute value. Then I don't need to memorize the equation for PMOS, right? And here I forgot to say that this is the W on L for P. This is the KP for P, right? And again, this is VGTP. I just put N here. This all has N and P times we set again absolute value of P, right? Minus we set of P square divided by 2. Okay, up to here, is this okay? The only thing that they're all math, but the only thing that I want you to pay attention is what is VGT, right? VG, if you look at the inverter, is the V in minus ground. So it is just V in, but V in is just VM. And then VGT means minus VTN, right? The threshold voltage. Right? This is for the left part. For the right part, everything is just like copying, except that now, what is VGT? Right? It is VGS minus VT. But VGS is what? I will take absolute value. So it's VDD minus V in, which is VM. Right? And then minus VTP. The whole thing, right? And then times V set P minus VD set. Yeah, I missed the D here. This should be D, right? VD set P square divided by 2. Is this okay? In terms of substitution. Now I try to simplify. You will realize that if you do it yourself also, I call something called R. Okay, I say R equal to KP dash sorry, actually I actually need to simplify a little bit more. Actually, this is different from what I write in the cheat sheet. This one, it is Kn, right? This one is Kp. Okay, so I simplify a little bit more. I say R equal to Kp, not Kp dash. Kp dash does not include W on L, times Vd set P divided by Kn times Vd set N. Okay. Now, if you try to do this substitution, basically, then you will find that you see, the reason that I do this is that I can pull Vd set N out. I can pull Vd set P out, right? So that's why this one divided by this one becomes R. And then I rearrange the terms, right? And then you will see that Vm equals to Vtn plus Vd set N divided by 2 plus R Vdd minus Vd set P divided by 2 minus Vtp divided by 1 plus R, right? This is not that difficult to see because when I pull up this Vd set N and pull out this Vd set N and Vd set P, and then this term become R, then you just recollect the term. You definitely will see I have a Vtn, also Vtn divided by 2. Vt set N divided by 2. Here is Vdd minus Vtp, and also have a Vd set P divided by 2. That's why you have this, right? And you have R. You just rearrange the term, you get this. So that is the VM that you will use to find the, this is the equation you will use to find the VM, right? So it is just math. It's not that important, right? But the important thing is you understand what I'm doing, right? So that you can do it for other equation in the future. If you have new equation, you can find it out. Why we want to do this? We can do simulation, but with this, we are gaining some insights we will see later. But any question on how I derive the VM?
Professor, can you explain why the VGTP is equal to VDD minus VM minus VTP?
Right.
Isn't it?
VGTP. Note that I'm using the absolute value, right? What does it mean? It means we just do it step by step. It means VGS minus VTP. Okay.
Okay. So for the VGS here, isn't that the VM minus VDD?
Right, but I take absolute value.
Oh, okay.
Yeah. So it's just EDD minus VIN. Yeah, okay. Good point, right? So why do I do that? Because it helped me to memorize the equation. You don't need to follow my approach if you don't like that. You just use the exact equation that the textbook give you. And then you just plug in, then you're right. VGS is VIN minus VDD. Then you probably will get negative VGS plus VTP, which will give me the same result. Right, so like what this student just asking, he already achieved the goal because he already know exactly what is the meaning, how to find the VG and VS, right? And then the rest it doesn't matter anymore. It's just you follow your approach. So if you can do that, then I think you don't have issue in solving this type of problem. Okay, any other questions?
Professor, so here we are assuming that the VDD is also at 2.5 and then VIN is is around 2.5. So what if like VDD is like 5 volts and then still I restrict my input to 2 volts?
No, to find VTN, right? It means that you switch the VIN from 0 to VDD. So you need to go to 0 to VDD, right? You cannot just say that. For example, let's say here, you say you restrict it to 1 volt, but that is not the VTC. You cannot just say you go here and then stop. because we need to sweep all the way to VDD for a VTC. Make sense? Do I answer your question or I misunderstood?
So I mean, like, when one of the voltages are not equal, right? So how do we do it? Like,
it won't be unequal. You need to be equal, because in any system you drive it, you come from the previous stage and they should share the same VDD, right? Unless you're saying that you have an interface from one chip to another chip using different system, then you don't have VM anymore. You actually have other matrix to make sure that you can turn it on and off. But now we're saying it is an inverter inside the same chip. So the input voltage must be VDD.
okay. So this might be in the midterm as well. So we had one curve, right, with respect to the VTC characteristic, where the x-axis was around 5, where the y-axis was only to 1 volts actually.
VTC?
Yes, yes. In midterm, one of the question was like the y-axis was around only 1 volts, and then the it was been like the x-axis was around 5 volts or something.
It doesn't matter, right? If you have more, your VTC is still VM equal to it just plot to you more. I mean, in reality, you need to have the same range, but they just plot more for you. It's not plotting less. Plotting more, I can still keep increasing V in. It's just that in the chip we don't have more V in, right? By definition, it's still V out equal to V in is the VM.
Oh, okay.
Yeah, even I
So,
plot more for you, it is still this point, right?
Okay.
Yeah.
So we don't consider the VDD by 2 there basically.
No.
Whenever it is.
No, not VDD divided by 2. It is when V in equal to V out. It's not VDD divided by 2. Right. So that's why the definition is very important. What for this curve, right? This is VM.
Okay.
Yeah, even it also go to 2.5 volt. But the best curve is VM equal to VDD divided by 2.
Okay.
Yeah.
Got it.
Yeah, and that also explains if it's always VDD divided by 2, why do I need to do this calculation? It's just VDD divided by 2. Okay, good. Okay, then let's have a deeper understanding on the parameter R, right? So this is the results, right? My writing was very messy, right? You understand that it's okay. And then this is the equation that you can use. Now, here you see that I did not use absolute value because they all take into account already. This is negative VTP, right? Here you see, I say minus absolute value VTP. So it depends on you. You can follow the textbook or use my approach. You should get the same result. Okay, just here, I just want to prove a little bit, right? We say R is equal to KP VD set P divided Kn VD set N is also equal to saturation velocity times the width divided ratio. So what does it mean, right? So let's recall again what is the saturation velocity. If I apply an electric field and then I have the velocity, the carrier is velocity keep going up and eventually it's saturated, remember? And we call this and I need to make it curly, right? So you know there is saturation velocity. It is not the voltage. And we say that at the point where it saturates is when the electric field equals to the critical electric field. Okay, so from here, what is R? What is Kp, right? Kp is W on L P mu P CMOS times V. This is the saturation voltage divided by W on L N mu N CMOS. And this is the saturation voltage of N. Is this okay? Now, but then in a transistor, right, I have a length L. And then if I say that this is VD equal to the saturation, then basically it's saying that the E field, right, is almost equal to VD divided by L, right? Voltage divided by the length, which is equal to VD set divided by L. And this is called critical electric field, right? Because this is just at the voltage at the electric field where it got saturated. So as a result, right, let me call this 1, this is 2, so you won't get confused in the future. Then it means VD set is approximately equal to the critical electric field times the length. Okay, so this one becomes what? W on L P mu P CMOS critical electric field of the P, all right, for the whole times L P divided by W on L N mu N CMOS critical electric field of the electron times Ln. Is this okay? Then L got cancelled. CMOS are the same. And then we just say that the mu P from here, right? Here, this is the mu. Mu times the critical electric field is just equals to the saturation velocity. So this is just the saturation velocity of P. And this is just the saturation velocity of N, right? So because of this, this is equals to WP, saturation velocity of P, divided by Wn, saturation velocity of N. And that is what we have here. Right? So we do this derivation, we try to clear a concept again. Sometimes we need to do approximation, right? So you need to understand that, hey, of course, this is not exactly correct, but basically VD set is meaning just to mean that when your VD reach VD set, it is in velocity saturation. Then it means the critical electric field is just equal to VD set divided by your length. Right? And similarly, the so-called saturation velocity is just the critical electric field times the mu, right? Just this triangle, this linear relationship. And that's why this R is also equal to this, which will be useful in the future derivation. And you can see that based on this, we can try to change the VM. Okay. Any question on what I'm deriving? Okay, if no, then now we know what is VM, how to derive VM, right? So we can rearrange the term just to find out how we should size the VP divided by the WP divided by WN so that we have different VM. What is your conclusion from this? It goes from, this means that, here means that WP equal to WN. Here means that WP equal to 10 WN, right? So I increase the ratio by 10 times. The VM only increased by about 0.4. So it's not very sensitive in the nowadays case, right? So what is the good thing about not sensitive? They always the same. Then it means that I can use smaller WP to achieve similar VM, right? For example, your boss, your customer say that, hey, I want to have a VM equal to 1.3 volt. Then you say, wow, I used the equation. I found that the WP need to be 40 times, right? WP is 40x of WN. That is very wide. But then you say, hey, maybe you don't really need 1.3, is 1.2 okay? Maybe 1.2 is okay. You persuade them and you relax other requirement. You do something to fit it. Then you do 1.2. I don't know. What is this? Maybe 25 times or something, or 22 times, right? You save half of the area by tweaking this one. Okay, so you don't need to stay with this one, right? But of course, there's a disadvantage when you cannot control it well. It means that when you want to control, you cannot. So it is difficult to change VM by WP over WN. So in your project, right, you are all doing with the 45 nanometer technology. Let's say you want to make it symmetric. You realize that it is difficult. You need to increase a lot or decrease a lot in order to get the VM that you want. So you need to resort to other methods. Okay, let's do an example, right? How to find the WM, right? So here is the equation that is given already. How should I size it? Size it so I can get the VM at the middle. So here is given, it say that find VM equal to middle of the rail. So what value do we want when VDD is 2.5? What is the meaning? I mean, what VM should we set now for this question?
1.25.
Why?
VDD by 2.
Thank you. Yeah, I'm just asking something very straightforward, so you may doubt about yourself. Why it's so easy? 1.25, right? So it's easy, indeed, this example. So W on L on P divided by W on L on N equals to Kn dash, right? We look at Kn dash 115 times 10 to the power minus 6. VD set N is what? 0.63, right? At the table below. VM, this is what we need, 1.25 volt. VTN here, 0.43. And then minus VD set N, which is here, 0.63 divided by 2. And then the whole thing divided by KP dash. Right here, I will just use negative value because I know I won't mess up. Or you can use positive value. And then I plug in, what is that? Next one, VD set P, which is -1, right? Again, I need VDD 2.5, VM 1.25, VTP -0.4, and then VD set P -1 divided by 2. Okay, and just do some calculation, is 3.4. 3.48, right? So you need to size the PMOS pretty large in order to get the middle VM. Any questions?
So this sizing methodology is for an inverter only?
Yeah, for an inverter, but yes, for this equation is for inverter. But the insights you get from here, you can apply to other things, including NOR gate and LAN gate. If you ignore the body effect, a series transistor is just a longer transistor. A parallel transistor is just a wider transistor, right? So the insight you get is still the same.
But we cannot apply to like an amplifier, correct?
No, no. Depends on what you mean by amplifier. An inverter is also an amplifier. But what we are talking about here is to size it to the middle. This is the DC, not AC analysis.
Yeah, I was referring to like a low noise amplifier, but I got it. Understood.
Right, this is digital, yeah. But the biasing point is still the same for no noise amplifier, whatever, right? Depends on your structure. Remember, we derived this by writing the IN and IP. We did not consider other things. So you have, your circuit has other components. You need to make sure this equation is still applicable. Okay, so we know how to calculate VM. We know how to size it, right? So why VM is so important? That is just because, look at this, depends on your application. For example, your input might have a lot of noise when it is at low part. Then in that case, you might want to shift your VM from VMA to VMB, right? If you use VMA, then this noise sometimes will bring it back to the high, and then your output will be very noisy. But if you make the VM close to the VDD, then this noise won't have effect, right? So VM, of course, at the same time, it shift your noise margin also because it affects VIL, VIH indirectly. Okay, so sometimes depends. But if you have noise from both sides, then no, you need to think of other way. But you are very sure that the noise only appear when the input is low, then you can shift it higher to help you, and vice versa. Okay, because whenever your signal cross the VM, it's going to switch.